All right, we'll have a look at CMMs, or coordinate measuring machines. So this is an example of a CMM. This is one of the CMMs that we have in the metrology lab. So what is this thing? It's a coordinate measuring machine, and what it's able to do is, you notice how it's, it kind of looks like you've got X, Y, and Z axes of motion here, which you do. And what you do on this thing is you drive a little tool around, and when that tool bumps up next to a part, you get a measurement. And so you can get measurements all over a workpiece, and you can get measurements on opposing sides. You can get things like a distance or features of size, things like that. So these things have two major roles, and by an overwhelming margin, inspection is the more important, more popular role of a CMM. So this is to measure work pieces to make sure that they are within tolerance. The other role that these things play is they're useful for reverse engineering. So say you have an object and you want to duplicate it, you can go in and get measurements from it and replicate those in CAD software. Alright, so like we said, you can get all kinds of different types of measurements, measurements of size or shape, or of position or orientation. So this would be things like angularity. You can get things like shape profile. You can get a position tolerance, and features of size. So really anything that you could do GD&T on, you can evaluate with a CMM. All right, so this is the general arrangement. You have a probe, and the probe, at least most probes, just have an on-off sensor, essentially, that tells the CMM that this has touched something. Now, you could walk up to this probe and touch it, say, down here, and all it would know was that it touched something. It would not know that you touched it over here in this location. This end down here is just a sphere of ruby material in general. There are others, zirconia and other types of materials that you could use for a probe, but it's just like a ball of glass down here. All right, it doesn't have any kind of sensors on this sphere down here. So how is it able to know where to put the point? The point right here in the middle doesn't make much sense. That's not very useful. What you want is the point on the extremity, on the outside of this. And the way that the CMM knows that this is the point of interest is that the CMM would have been traveling toward this surface when it touched it. Okay, and so it will infer, based on the fact that it was traveling in this direction, and the fact that it knows the size and really even the shape of this sphere down here, it can calculate that the point that it should record is out here on this surface. So what it has to actually record is not just the fact that it touched this surface, but that it was traveling in this direction toward this face when the contact occurred. And the way it keeps track with that direction is with a vector. Okay, so every CMM hit point, every measurement, has got a point and also a vector associated with that point. So this works out really well, if you have nice flat surfaces that are perpendicular to the axis that you're traveling in. All right, so if we were traveling in this direction, straight on, completely perpendicular to this surface here, and we trip the probe, then it knows to put a point right there with a vector pointing out. Now notice that the vector on this surface is normal to that surface. All right, and that's you can actually tell a lot about that, and we'll talk more about these vectors here in a minute. But let's drop down here and consider this condition. Okay, let's say that we're trying to probe this angled surface, and we travel in this direction, and all of a sudden we trip the probe. Well, the point that we would want would be this one. It would be at the point of contact. But the point that we get is this point out in space here, because the probe was traveling in this direction, and all it knew is that it was tripped, that it touched something. And so the CMM's a little stupid, and all it could do is just assume that it touched a vertical surface like this. That's kind of the way that it's made to think. Well, obviously this is not going to do. We're going to have to do something else to be able to handle situations like this. Because, actually, truth be told, this surface is not perfectly aligned with the axis of travel. All right, and how do I know that? Well, because there is no perfectly aligned surface that's going to align perfectly with the axis of travel. All right, this is metrology, and metrology is a world where there's no, if it's an actual part, there's nothing perfect about it, ever, by definition. The only perfect geometry is the mathematical geometry. All right, so let's have a look. So this is maybe a slide I should have had earlier. This is how the controller keeps track of how far it's, or how the CMM keeps track of how far it's moved in a particular direction. It actually records its motion with these things called encoders. So encoders are kind of like a picket fence, you know, and as you go along that picket fence, you're able to count how many pickets you went past, and you know how far you've traveled. All right, but let's talk a little bit about those vectors. You are probably used to vectors having an angle or a direction and a length. So they have a magnitude and a direction. In this case, though, we're not so interested in the vectors having a magnitude. The only job that we need the vector to do is to keep track of a direction. All right, so we use what's called a unit vector, a vector that has a unit length of 1. And the way that we will define these vectors are by their components. And we'll call the components the I, J, and K components. And these align with the X, Y, and Z axes of the coordinate system that we're going to be in. All right, so you'll have 3 numbers for any vector. And so really for any point, I should, let me drop down here. So for any point, you'll have 2 things. Number 1 is you'll have the 3 coordinates of the position. So in this case, this point is located at 15 in the X, and then -4 in the Y, and -4 in the Z. So that locates the point. But the other thing that goes with that is the direction vector. And here you see that direction vector is pointing in the negative X direction. So its I is -1, its J is 0, and its K value is 0. So that tells us that it is completely aligned with the x-axis. And you might say, well, that seems unrealistic, because we just got through saying that this face on here is not going to be perfectly aligned with the x-axis. But keep in mind that the machine, even if we were jogging slightly in 2 axes at one time, when we probed this point, he would snap this vector to the nearest axis of motion. And so it's pretty common to get vectors like this when you're probing manually. But I guess I'm getting a little bit ahead of myself. Let me back up here. All right, so what you need to realize when you have those 3 vector components, you have the I, the J, and the K, what you really get from that is look for the biggest one, and that tells you how closely or which axis the vector is mostly aligned with. All right, so let's say that you had a vector, let's say we had a point and a vector that looked like this. Okay, this is its X, Y, and Z location. This is the location of that point, and this tells us something about how the CMM was traveling when it touched that point. All right, do you know whether this point would be on the front side, the left side, the top, or the bottom of the object? All right, and what this tells us is that the point, this 12, 4, 10 point, is located on the top of the part. All right, how do you know that? Well, this is our I, and that aligns with the x-axis, and it's not at all aligned with the x-axis. It's not at all aligned with the y-axis, but it's pointing straight up. All right, and since the vector is pointing up, that means that the probe was traveling down when it touched the surface. So this tells us that this point at X, Y, Z 12, 4, 10 is located on the top of the part. All right, but remember we said that that's not going to align perfectly with the part, and we still have this problem here that we have not solved, where we bump up against an angled point and we get this incorrect vector. Sometimes this is a situation that will solve itself, okay? For instance, if we're probing a cylinder and we take all of these points on the cylinder and we tell the CMM, hey, that looks, look for a cylinder out of these points, then what it can do is, even if you didn't probe these exactly traveling in, and you actually can't manually do that, you cannot manually drive perfectly normal to this surface like this, but if you took enough points around here and said, hey, do you see a cylinder, then it would do some best fit analysis and it would fit a perfect cylinder to those points. And once it realizes that that's a cylinder, he says, well, at this point on the cylinder, the vector must be pointing in this direction, and the CMM will correct all of those vectors and shift the points to where they would be if it was probed perfectly. And so when you probe features like this and you generate features from those points, then that misalignment gets taken care of. All right, so what you can do is use this technique to actually build a whole reference frame that your part exists in. So one of the things that you do with GD&T is you set up different datums to establish a coordinate system. You establish what's called a datum reference frame. And once you have that datum reference frame, you can do things like talk about where the true position of a feature should be, and you can give it a position tolerance and tell it, the true position where this should lie is located at thus and so inside of this datum reference frame. So what you do with a CMM is to set up where your X, Y, and Z will actually align with your part, is to go through a procedure of creating these things called alignments. Okay, so notice that here, if we probe these 2 points, even though the points weren't probed exactly right on the surface, we can at this point say, that is actually an axis, and align the axis to that. All right, so that will allow us to set up a frame like this, and now we can actually jog and precisely probe points like that. All right, and so you'll use alignments not just for obviously crooked parts like this, but you'll actually set your part in the CMM, and when you load your part in the CMM, there's no guarantee. In fact, there's a guarantee that it's not exactly perfect. Okay, that part is guaranteed. But so you have to actually probe the physical part and align the reference frame to the actual physical part. And the way you want to do that should mimic the datum reference frame as it is spelled out on the GD&T in the drawing. All right, so we'll come in here. This is the way that these alignments work. I showed you an example that kind of looks like two-dimensional alignment, but in general what you'll do is come in here and set up a three-dimensional alignment. And what you'll have when you've done that is a thing called a part coordinate system. Or from the GD&T side, you can think of it as a datum reference frame. And the language that's used in PC-DEMUS is to talk about level, rotate, and origin. So when you level, you take this coordinate system that right now is undefined, okay? And in fact, in PC-DEMUS, this thing will be sort of dancing and pitching around to show you that it can move, that none of the degrees of freedom of this coordinate system have been defined. They haven't been constrained at all. And so in general, the first step is to level one of the planes of the coordinate system. And which of those planes, whether it's the XY or the XZ plane or whatever, that's up to you. Okay, so we'll say that we want to align this, the XY plane, with the top of this part. Now, of course, the top of this part is not perfect. It's an actual part. It has actual geometry. But what you do is probe it enough so that the CMM will best fit a plane to this plane. It will create the true geometric counterpart to this surface that only approximates a plane. And once you've done that, we can level this plane to the plane that's created from the geometry. All right, and then what we'll do, so first we level it and it will snap into place like this. Now what can happen is this thing can translate up and down and it can twist, but it can't tip. All right, so it's locked into this vector now. It is leveled. The next thing to do is to rotate. And so at this point, we twist the coordinate system until it aligns with something. So we could have a planar feature here, or we could have a line feature here, and tell it to align one of the three axes, the x, the y, or the z axis, with that feature. All right, so that's the second step, is to rotate. And then the last step is to origin. All right, so that means we have to tell it physically where the origin point is. And with those three things defined, we can then, we now at this point have a coordinate system. We have a part coordinate system. And where we put that, like I said, should align with the way that the datum reference frame is called out in the GD&T. You know, datum A, B, and C, that kind of thing. All right, so in general, a lot of CMMs have what's called DCC control. Okay, more often than not these days, CMMs have what's called direct computer control, and this is sort of like CNC, where you control the tool completely by the computer. In general, what you do is you put a part loaded into the CMM, and then your program will hopefully say take a hit point, or take hit points in a particular location, and that will help the CMM to understand where in general the part is laid out. And then generally, once you've probed that first manual point, you don't always have to program a manual point, but it's in general a good idea. If you're doing a lot of production with a fixture where everything's going to be in the same spot over and over again, you can get away with not doing it, but you didn't hear it here. But anyway, you let the DCC take over, because the DCC will probe very consistently. And that's in general what you want to do, is you want to do manual as much as is appropriate, and then switch over to DCC mode, and you'll get really nice repeatable results. All right, let's see. I'm gonna talk about the probe speed. If you're in DCC, then generally, then the probe speed is going to be really consistent. But what you want to be careful of when you're calibrating, you don't want to. You can calibrate once in turtle mode. You can calibrate in a slow motion, but when you get ready to calibrate, I guess I should really talk about what calibration is here. We'll talk about it in a minute. But when you calibrate, you really want to calibrate at the same speed that you're going to be taking the measurements, because that can affect the speed. And actually, this slide, truth be told, should be a little lower down. All right, so keep in mind that the probe, all of this stuff is insensitive. It has no sensors in any of this. There's only one sensor up here at the top that knows when this has been disturbed, okay? And so if you bump into a part like this with the shank of the probe instead of the actual stylus down here, then you can get a false reading. So this is called a shanking error, where you've bumped into the shank instead of down here on the probe itself, where you're trying to get that. And this is the result that you'll get from that. You'll think that you have this point, which is the one that you want, but what you'll in fact have is a different point. All right, so this is how you calibrate these spheres. So the little rubies on the end of these are not perfect spheres, and what you want to know is what is the exact size of this ruby down here. So rubies they don't really have gauge ball accuracy. The thing that does is this thing called a qual sphere, or calibration sphere. So this sphere is made to a very refined sphericity, and it's made to it has a very well-known size. And so what you can do is characterize this probe by probing on this other sphere in a lot of different points, and the software will compensate for this. So it will know that if it's probing on this side, to add 0.029 inches, or that is equivalent to that far off of the sphere center. And so it will adjust for that. So it characterizes this probe. All right, so we'll kind of get our bearings here on the different types of geometry. We have sort of the mathematical, the nominal geometry, where we say we want a box that's 4 inches across and 1 inch thick, and it has a 2-inch hole in the middle. We talk about this, as being a cylinder, and this as being a rectangular prism. Well, real geometry, or actual geometry, is nothing at all like this, okay? It might look very nice, it might be very well manufactured, it might have a near mirror finish on it, but in fact it's imperfect, all right? It's just the fact. It is not a perfect part. It might be well in tolerance, it might be very, very much in tolerance, but it's not perfect, okay? It's good enough. All right, and what you can do is take that actual geometry and probe it enough, and then, like I said, you can do this best fit analysis and fit planes to these surfaces. You can fit spheres or cylinders to these cylindrical approximations of cylinders. And what you can do is bundle those points together into these associated surfaces. All right, so you have these different types of geometry. Now, the steps where this geometry is important, you kind of go through different workflows depending on whether you're doing reverse engineering or inspection. So inspection, since it's the more typical application, we'll start here. We start with a CAD model, for instance, of the perfect geometry. We have our actual geometry. We probe it, get these points, and then we fit surfaces to that. We fit a series of planes and spheres, and sometimes circles and lines. What you should realize, a lot of students don't, they kind of imagine that if they probe this thing enough that it will look like a solid model, and it doesn't really start that way. You wind up with a plane and a plane, but these are generally sort of unbounded planes, and what you have to do is use the information from these to work back if you want to create a model. So if you're reverse engineering, you start with the actual point, you probe it, and you don't get a model down here. You get planes and cylinders, and you have to work that the values from that geometry into a CAD model. All right, there is this thing called a work plane, and I'll just discuss it because you can get some surprising results in something like PC-DEMUS if you're not aware of how a work plane works. But generally, the work plane is the plane through which PC-DEMUS, or whatever the software is that you're using, is looking at the geometry, the points that you're probing. So here, if we probe 2 points and we said put a line between those 2 points, you might expect that point to be tipped down like this, but if we have this work plane active, what it will do is find the sort of the geometric center of where that line is, sort of the centroid of that line, and it will put the line at that level aligned with the work plane. Okay, and I have a lab where I actually have you probe some points and you get some surprising results. If you don't know how a work plane works, then you might be confused about the way you get those points. But that's actually in Tech 4571, so that's or 4476, the CAM class, we do that. All right, you can also insert points for the probe to just move to in order to avoid collisions, and you can install or put in what's called a clearance plane so that you move up to this sort of safe plane to avoid bumping into other geometry. I'll just say it's the easiest thing in the world to crash a CMM. So if you're not taking a few cautionary steps, and when I say it's easy to do, it's also easy to avoid if you take the right steps. So don't let it happen. You can avoid crashing a CMM. All right, so there are some good best practices. You never want to treat a workpiece as an actual measuring device. So you want to be aware of that that the planes that are on that workpiece, you can do alignments to those planes, but you need to understand that the planes themselves, or the surfaces themselves, are not the measuring surfaces. You'll take measurements from them. You'll want to keep the setup clean, and you'll want to keep your programs nice and clean. All right, you want to make sure that everything's nice and simple, and for heaven's sakes, have everything documented. Don't just say things like probe the part. Say things like probe the part as documented in setup sheet number 1001 or something like that. You need to be very clear about where to probe the part, is what I'm saying. Oops, got ahead of myself. Make sure the programs are neat, organized, and logical. Also, here's a news flash: a CMM will lie to you and give you bad information. Okay, I don't mean that they don't function well, but I mean that they function very precisely, and it will tell you exactly what you ask it. And so if you ask it a question, like you take 5 points on a surface and you say, is this surface flat? It might very well say yes. Okay, but that's going to depend on the 5 points where you chose to probe that thing. And if you're trying to evaluate flatness with 5 points, then that's probably not the best way. So be careful. The CMM will give you the exact answer that you ask. And be careful of inspection sheets that say that a part is good. There is a very real tendency to take a report that comes out of a CMM that says that a part is in tolerance or out of tolerance, and that is generally the last word. That has to be validated ahead of time, though. You need to make sure that program, when it tells you that a part is in tolerance or the part is out of tolerance, that it really is. Do not just blindly trust a CMM. Be very careful of that. Let's see. Also, and we talked about having good setup instructions and things like that. There is also in PC-DEMUS some language about measured geometry versus constructed geometry. So if we were probing this point, all these points on this surface, and we created this plane object, then that would be measured geometry. If we did the same thing over here and we measured this plane, that would be measured geometry. But what we could do is say, I'd like to create a line, please, or where these two planes intersect each other, and it would construct a line element based on where these two planes that were measured existed. And so that would be constructed geometry. You see, you could find where these planes intersected in this direction and construct an axis or a line there. So that's the difference when you see it's asking about measured geometry or constructed geometry. That's the difference. So at the end of these slides, there are some CMM videos. Just get out on YouTube a little bit and look at some of the stuff that CMMs can do and kind of get familiar with the idea of this. But that's all I've got for now. There is an NX exercise where you go through and do some inspection of a part, so make sure that you do that.